So here we go. They're going to finish the race down here. It's pretty obvious at this point who's going to win the race. The guy up in lane 5 is going to win, as well, they're not getting tired. They're moving at constant rates of speed. So once he's ahead and he's moving faster, he's going to continue to be faster all the way to the end. So we can wait and play this out. And actually, he didn't run 100 yards in 12 seconds. But we'll assume he was going to win anyway, and I'm not going to go back and rechange the window. If I change the window, we're going to have to watch it all over again. So what I'm interested in is who is ahead after 3 seconds, and by how much. If I trace, okay, let me bring this up close again so we can see. Start to move left and right. You can see the time incrementing. Right now we're at a half a second. Okay, now we're at 1 second. So let's go all the way out to 3 seconds and see where this guy is at 3 seconds. Okay, so at 3 seconds, he is, you can kind of see that, 3 seconds he's at 60 feet. Okay, now let's see where the guy in lane 5 is. We can just press up and he'll jump up there. Look at that, at 3 seconds he was at 62 feet. Okay, that's all we need to know to answer this question. So who was ahead after 3 seconds? After 3 seconds, the guy up in lane 5 was ahead, and he was ahead by 2 feet. Notice the X value changing from 60 to 62. Okay, so I would write, so let's see, Ben was ahead. I know it's Ben. Ben was the one that was going at 24 feet per second, and he was also the one that was up in lane 5. So Ben was ahead by 2 feet. And of course by then he just cruised to the victory. Next example problem says, a baseball is hit straight up from a height of 5 feet with an initial velocity of 80 feet per second. Write an equation that models the height of the ball as a function of time. So we need kind of our position function for part A. Alright, S of t equals 1/2 gt squared plus v sub 0 t plus s sub 0. In this position model, g is the constant of gravity, the accelerational the gravitational acceleration constant. Since our units are in feet, in this particular problem we'll use -32 as our approximation for g. V naught, v sub 0, that's the initial velocity, and the problem tells us that's 80. And s sub 0, s naught, is the initial height, so 5. So we get an equation -16t squared plus 80t plus 5. Okay, part B says use parametric mode to simulate the pop-up. So a lot of this is going to be done on the graphing calculator now. So going into the graphing mode, we're in parametric mode. For the x, I'm going to just kind of pick a constant. I'm just going to use 3, but we could choose any constant. Kind of using the x as kind of like the lane or the track that, you know, from the last problem that like the runners were on. But since the ball is going vertically, we need kind of a vertical track. And underneath the y, I'll type in my position equation. For the window, I've already set this up. So you can see a little better. 0 to 6 should work. For the x's, I just put 0 to 6 because I really just want to see that one lane of 3. So I just kind of went a little less and a little bigger than that. And for the max, I played around with it a little bit and I got 150 as a y max should be sufficient. In other words, the ball is not going to go higher than 150 feet. And when we hit graph, you can see the ball going up. And then eventually it reaches the top and it's a pop fly, so of course it starts to come back down the screen. Okay, that's part B. It's just all on the calculator, nothing to write down on paper. Part C says use parametric mode to graph the height against time, and it gives us a hint. Let x of t be t. So if we go back to the y equals, instead of letting the x be a constant, which is going to mean that the height is always showed over a constant, just went straight up and straight down. If we change that to t and hit graph, well, now we'll actually see kind of the path of the ball, the path of the pop-up, I guess. Now, part D asks us, how high is the ball after 4 seconds? So to answer that, I'm just going to hit trace. Come a little closer so we can see. Hit trace. And notice I've got the x, y values, but I've also got a t value, and t is time. So I'm just going to trace on out till I get to 4 seconds. And right there, at 4 seconds, the ball, you can see here, the height, the y value, is 69 feet. So for part D, 69 feet. Part E, what is the maximum height of the ball? How many seconds does it take to reach its maximum height? Okay, so we can calculate the maximum, if you recall, by doing second calculate. Actually, in parametric mode, that's not going to work. Sorry. Let's just go back to the graph, and we'll just go ahead and trace it on up. I think we'll get close enough just doing that. So I'm looking at the y value. See, it's 101 now, 101.76. It's still going up. Still going up. Right there. It's at its peak, 105 feet. And look at the time, that took 2.5 seconds. So there's our answer to part E. The maximum height, 105 feet at 2.5 seconds. Alright, this last example reads, Tony and Sue are launching yard darts 20 feet from the front edge of a circular target of radius 18 inches on the ground. Let's just maybe draw that. So here we've got this guy. He is 20 feet from the circular target on the ground, and he's throwing yard darts. And so the question is, he's throwing yard darts. Is the yard dart going to track and land into the target? Gives us some extra information. He throws the dart directly at the target, releases it 3 feet above ground with an initial velocity of 30 feet per second at an angle, at a 70-degree angle. Will the dart hit the target? Very similar to the last problem in that we've got information like initial velocity, an initial height. So it kind of leads me to think that we're going to use that projectile motion equation from the last problem. But the difference is, in the last problem, there was the ball was just a pop-up, went straight up and straight down at an angle of 90 degrees. Here we've got an angle other than 90 degrees. Now in order to do this problem, we have to understand that the initial velocity of the projectile, in this case the yard dart, can be represented by a vector. V naught cosine theta V naught sine theta. The path of the object can be modeled parametrically by the following equations. X equals V naught cosine theta times t, and then here y is your projectile motion equation. I'm going to go ahead and just put in the negative 32, right at negative 16 t squared plus V naught sine theta times t plus, and I'm going to go ahead and just use y sub 0. Instead of s, I'm using y because I wrote y over here. So it is very similar, except we've got kind of this horizontal component of our initial velocity and the vertical component of the initial velocity vector kind of within each of these. Okay? So with this, we should now be able to write our equations. Our x equals equation is going to be initial velocity is 30 and the angle is 70, so it's going to be 30 cosine 70 degrees times t. The y is going to be negative 16t squared plus 30 sine of 70 degrees t plus, and then the y sub 0 is the initial height, that's 3 feet above ground. So here's our system of parametric equations. Let's go to the graph and see what this produces. Clear out the ones from the last problem. We've got 30 cosine 70 t. We've got negative 16t squared plus 30 sine 70 t plus 3. As far as the window goes, I don't know about the t min and max. I mean, 6 means 6 seconds, so that might be good enough. It might not. We'll just leave it at that for now. Why not? The x maximum, well, the x, that's the horizontal distance, and we know that we're standing 20 feet from this target. So I'm just going to go a little bigger than 20 feet. I'm going to go maybe 23 feet. The reason being is if I'm 20 feet from the front edge of the target and the radius is 18 inches, that's 1.5 feet, means the target's 3 feet in diameter. So 23 feet would be the back edge of the target. So that's just going to be the edge of my calculator screen. For the y values, well, the y, that's the vertical height of this yard dart. I don't know that it's going to go 150 feet, so I'm just going to put 50 and see if the screen contains the graph. But let's go ahead and hit graph and see what happens. So there's the yard dart, and now it's hit the ground. Okay, so let's see. Well, if the edge of the screen here is 23 feet, and we know that the diameter of this target is 3 feet, we can count back on the tick marks, and we can see that the dart did in fact not hit the target. The dart is short of the target. You might even go back here. If I go to window, maybe I make the X max 20. Okay, so now the front edge of the target is right here at the edge of the screen. And we can see that the dart did not make the edge of the screen, therefore the dart did not make it into the target. So, will the dart hit the target? Answer is no, it will not hit the target.